This video is about resistance sensors other than thermistors, other than temperature sensors. It corresponds to sections 5.4 and 5.5 of Applied Analog Electronics. Now, some of the ones that you might encounter, some of the resistance sensors that you might encounter include photoresistors. And they're generally symbolized as a resistor symbol with an incoming arrow, which may be wavy or straight, to indicate that light changes the resistance of the photoresistor. Photoresistors are commonly made out of cadmium sulfide, which ends up having a spectral response very similar to the spectral response of the human eye. And so these are very popular for things like the ambient light sensors that you get in laptops that adjust how bright your monitor is based on how bright the room light is. They're not very popular for some of the applications we have for photosensors because they're very slow. And so we'll be looking at photosensors later on in this course that are not photoresistors. But photoresistors exist and do have some common applications. Another type of resistor that we'll be looking at are piezoresistors. Now, the piezoresistor is one that responds, according to the name, to pressure, but in fact what we really have for most of them are strain gauges. Which respond to changes in the length of a piece of material. And so as you push or pull on a piece of material, it gets longer or shorter. If there's a piezoresistor attached to that, strain gauge attached to that, the resistance of that strain gauge changes based on the stretching or squeezing of the material. And we'll encounter them in this class mainly as being internal to the pressure sensors we use. We won't be directly using a single piezoresistor, but we'll be using pressure sensors that incorporate piezoresistors into their operation. Perhaps the most interesting one from a biology standpoint is the chemiresistor. A chemiresistor, as its name implies, changes its resistance based on some chemical detection. And a lot of these are gas detectors. They detect things like alcohol, carbon monoxide, methane, hydrogen. And these chemiresistors are very cheap sensors that get used in things like carbon monoxide alarms in houses and in a lot of hobbyist applications. The hobbyist version of a breathalyzer generally uses a chemiresistor. The professional ones tend to use a different detection technique, a fuel cell approach that is more precise but more difficult to build the circuitry for. So let's take a brief look at how chemiresistors like alcohol sensors work. And the basic idea is that we have a semiconductor, usually tin oxide. And the tin oxide is a semiconductor because there's usually a slight excess of tin, which acts as electron donor. So you have a slight shortage of oxygen atoms. It's not pure tin oxide. This substance is very sensitive to things being adsorbed onto the surface. You generally have a thin layer of the tin oxide. So if you're measuring the resistance, it's how many charge carriers do you have. Well, if you change the composition of this material just a little bit, you can change those charge carriers quite a bit, and so change the resistance. And in particular, what the tin oxide sensors usually have is a little heater. You heat them up in an atmosphere that contains oxygen, and that adsorbs some oxygen onto the surface of the sensor. That oxygen then ties up some of those free electrons and increases the resistance. So once you heat the thing, you heat it in the presence of oxygen. And that gives you sort of a high baseline resistance. Then if you have a reducing gas, the gas that you're trying to detect, it will either interact with the oxygen that's adsorbed onto the surface, or it'll interact perhaps directly with the tin oxide, and it will free up some electrons, and now that decreases the resistance. So this sort of sensor usually consists of two parts. One is a heating resistor, and the other is a sense resistor. The sense resistor is this tin oxide, which is usually a very thin layer on something like an aluminum oxide ceramic substrate. And the sense resistor is what we're going to measure. But we first have to heat it by putting a voltage across this resistor and heating up the heating resistor, which heats up the entire unit. The device is usually designed so that you put a very precise voltage across this resistor and then wait a few minutes for it to reach equilibrium. And once it's reached equilibrium, then you measure the resistance of the sense resistor. And this heating is necessary because you need to adsorb oxygen onto the surface of the tin oxide and get it to a known temperature. The whole thing is temperature sensitive, it's humidity sensitive, it's got a lot of sort of minor problems with measuring things. Almost all the tin oxide sensors, the manufacturers design them to be particularly sensitive to one particular volatile compound like alcohol, but they nearly always have cross-reactivity with other volatile organic compounds. And so, if you've got benzene in the room, well, that's going to affect the measurement. And they're basically not very precise measuring units, but they can be very useful for things like emergency alarms and stuff, where you want to say, hey, I've got possibility of leaks in this room. I want to know, hey, is there any volatile organics in the air? You can make chemiresistors that are pretty good for that sort of thing. And like I say, the hobbyist breathalyzers, the ones that are not admissible in court, often use a chemiresistor that's alcohol sensitive. Now, true, it's alcohol sensitive. It's also sensitive to methanol, to benzene, and to other things that you're less likely to have on your breath. But you can buy these very cheaply from hobbyist supply places like SparkFun or Seed Studio, and play around with making your own breathalyzer, though not, as I say, a very good one. Okay, that's probably enough about sensors, resistance-based sensors. We'll be looking at some of these, particularly the piezo resistors in the pressure sensors, later on.